Today we're going to look at angular and linear speed, and to give you an idea of what the difference between angular and linear speed is, we're going to talk about the illustration of spinning something in a circle. So let's see how that works. So for example, angular speed, just to give you an idea of what it's like, think of a shepherd's sling, and you put a rock in it and you swing it around your head. As long as you're swinging it around in a circular motion, it's angular speed, because you're turning it around in a circle, and it's based on the angle of how many spirals you go. But the moment you let it go, whatever direction you let it go in, it starts going straight, and that turns it into linear speed. And so that's kind of what we're going to be doing. We're going to be moving something in a circular motion, but we'd like to know if we are going straight with it, how fast is it going? Now, some of the problems don't ask you to find both. Some of them do. This first example only asks for angular speed. And so let's look at the formula for angular speed and see how it works with this long roller. So the formula for angular speed is omega equals the number of revolutions over whatever your time factor is. Your time can be in seconds or minutes or hours, so you have to see what your problem's wanting for that. And you always multiply that by 2 pi radians over 1 revolution. And if you think about it, that makes sense, because a revolution means that you went all the way around the circle, and that we know that all the way around the circle is 2 pi. And why is it 2 pi is because if you go back and think about our unit circle with radius 1, 2 pi times 1 is how you find the circumference of a circle. And so therefore it goes all the way around as 2 pi, and we know that's what we label it from 0 all the way back around as 2 pi. So 1 revolution is 2 pi helps you to get part of the circumference to show the angle in radians at which you have turned. Sometimes you may turn a tremendous amount, sometimes you may not. Now here in this long roller, it makes 1.2 revolutions every second. So it turns all the way around and starts to go back around a little bit. It says to find this in radians per second. So we're going to start off by plugging in how many revolutions we have, 1.2 revolutions over seconds, because it says right here that that's the units that we're working with. Then we are going to multiply that by 2 pi radians over 1 revolution. Now, you cannot mess up how to put that fraction in, even if you don't remember the formula, because you wouldn't want to put revolutions on top. It wouldn't cancel with the revolutions you have. And that's kind of the whole point, is when you convert units, you want the units on the diagonal to cancel. So 2.4 times 2 is, 1.2 times 2 is 2.4 pi radians every second. Now we want to leave it in that format because omega, and we could change that to a fraction as well, but omega, you don't multiply the pi in, you leave the pi because it's radians, and radians are in terms of pi. Now this one didn't ask for linear speed, so we'll need to see another example in order to be able to do linear speed. So here we have a Ferris wheel. Its diameter is 50 feet. Now the moment you see the word diameter in a problem, the very next thing you should do is write down the radius and how much it is, so that you don't accidentally come over here and think, oh, that's 50. No, it's 25 feet. Then it says 1 revolution every 2 minutes. So it takes, by the time you get on, let's say you got on as the last person getting on the Ferris wheel, as they start the Ferris wheel up, it takes 2 minutes for it to go all the way around one time. So that's why when you're riding a Ferris wheel problem, you don't really end up getting to ride very long, because it takes so long for it to go around one time. Now ask for the speed of a seat on the edge of the rim of the wheel, which is where all of our seats are. And speed doesn't say angular speed here, so they're talking about linear, or what we call in science class velocity. And again, the difference between speed and velocity is speed is just how fast you're going, but velocity is how fast you're going and in what direction are you going. Now, in all of our problems right now, we're going to have a positive velocity because we're going in a forward motion. But in some problems, you might have a negative velocity because maybe you're dropping something and gravity's pulling it down. So we're not going to focus on any negative ones right now, so we can use those two words interchangeably. Linear speed or velocity mean the same thing. In order to find that, though, you've got to find your angular speed, because first you've got to figure out how fast it's going in a circle, and then you've got to figure out how fast it's going in a straight line. So we're going to take the number of revolutions over time and multiply it by 2 pi radians over 1 revolution. So our revolutions is it's 1 revolution every 2 minutes. We are multiplying that by 2 pi radians over 1 revolution. So as we do that, the 1 revolutions cancel. 2 divides into 2, so you want to cancel out as much as you can in these problems. So if you see a diagonal that cancels, cancel it. And so therefore we end up with pi radians every minute. So it goes halfway around every minute. Well, that makes sense if you think about it. Every 2 minutes it goes all the way around, and pi is halfway. Now let's talk about the formula for linear speed. So with linear speed, we use V for velocity instead of S for speed, because S doesn't mean speed. S means distance for position. So they use V for velocity or speed. And that's going to be omega times your radius over 1 radian. And it's always over 1 radian, because back when we started talking about the unit circle, we determined that 1 for the radius and 1 for the length of the arc will have a relationship called radians. So that's why we want to say it's over 1 radian. So we're going to take omega, which we just found a few minutes ago. Right here is omega. Omega is pi radians over 1 minute. And we're going to multiply that by the radius, which we said was 25 feet, over 1 radian. And then we see that the radians are going to cancel, but the pi doesn't cancel, just the radians do. And feet over minutes are the only units I have left, so now I know my units are going to be in that particular format. And also we can multiply pi times 25 and get the decimal answer for this. And we're doing 2 decimal places since pi is a 2 decimal place, usually rounded off, and get 78.54. Now, you may think, well, gosh, that sounds like it's going really fast. Well, remember, this isn't miles per hour. This is feet per minute. And let's go back and read the question. What was the speed of the seat on the rim of the wheel? It doesn't say what units they want it in, so I can leave it in feet per minute. Now, in some problems like this, it may tell you to convert your units, and they want specific ones, but this one did not, so I can leave it like this. And this is not a very fast Ferris wheel. So, for example, if your seat came off, maybe a bolt came out and it just fell off all of a sudden, you would be traveling at 78.54 feet per minute until gravity takes over to pull you down. That's what this means. All right, the speed of an object. We have a second hand on this clock, and this particular clock looks like it has a little bit of a second hand past here, but that's just to help balance the hand. The second hand is just this much of it. It says the second hand of a clock is 10.2 centimeters. So that happens to be our radius. It says find the speed of the tip of this second hand. So we'd like to know how fast the tip's going around the clock. So first we've got to start off with angular because we're going to be able to find regular speed, which happens to be velocity. But you can't get there without starting with angular. So we start with omega, the number of revolutions over time. If you write the formula every time, you will have no trouble remembering the formula because you've written it so many times. But don't look it up every time. Try to write it from memory every time. Now, I don't have how many revolutions this is, so I have to think about how long does it take for the second hand to go all the way around the clock. So it's up here at 12 right now, so it'll go to 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds before it gets to 1. So it's 60 seconds all the way around, or it takes a minute. Now, they don't tell me what units they want it in, but I don't think they wanted to put it in a minute format. Since we're talking about a second hand, we should talk about seconds. So it's 10, not 10. It's 1 revolution is 60 seconds. Each time it goes around all the way, it took 60 seconds to do that, to go 1 revolution, to go 1 time all the way around. So now I can cancel the revolutions. I can say 2 goes into 60 30 times, just using our fraction reducing possibilities here, and I end up with pi over 30 radians per second. Now, once I get my radians per second for omega, remember this is the letter omega from the Greek alphabet. So angular, anything about angles is always using Greek letters. So when we want to do linear speed, we use our alphabet and say the velocity is equal to omega times the radius over 1 radian. So I take my pi over 30 radians per second. I multiply that by the radius. Now we just labeled our picture over here that the radius is 10.2 centimeters, and you have to put that over 1 radian. That's the only way these radians are going to cancel out. Now the only units I have left are centimeters over seconds. So I'm trying to figure out how many centimeters a second it is. So I multiply pi times 10.2 divided by 30, and that gives me 1.07 if I round it off to 2 decimal places. Well, let's go back. I wanted to go back up and read the question. Find the speed of the tip of the second hand. It doesn't say what units that they want that in. So this 1.07 centimeters a second is perfectly fine for our units. So now we're going to look at something rounded to the nearest 100 miles per minute. So they're telling me my answer has to be in miles and it has to be in minutes. So if that's not what they're giving me, I would need to convert. What is the speed? Okay, again, speed means velocity. Of the Earth's satellite traveling in a circular orbit that's 600 miles high, well, that means that it's 600 miles from here to here above the Earth's surface. If it completes 1 orbit every 80 minutes, so that means it went all the way around the Earth in 80 minutes. Well, the Earth has a radius of 4,000 miles. We've been using that for a while. All right, let's start off with angular speed. So omega is equal to the number of revolutions over time times 2 pi radians over 1 revolution. So if I plug that in, it told me an orbit is 80 minutes. That means it went all the way around. So an orbit and a revolution mean the same thing. So 1 revolution is 80 minutes. 2 pi radians is still already in the formula, so I just rewrite that part so that revolutions cancels out revolutions, and 2 goes in 80 40 times. So I get pi over 40 radians over minutes. Now my final answer is supposed to be in miles per minute, so at least I've got minutes so far. I don't need to change my time factor yet. All right, let's go back over the formula for linear speed. Velocity equals omega times the radius over 1 radian. So I have pi over 40 radians per minute. I know I'm going to put it over 1 radian, but I need to discuss, well, what is the radius of my circle? Where is the center? Well, the center is right here. And from there to the surface is 4,000. So my radius is 4,600 miles, because I have to add the radius of the Earth to the amount I'm off the Earth, so that I'm all the way to the center of the circle. So 4,600 miles. So now I need the radians to cancel so I can get miles per minute. And I will take 4,600 times pi divided by 40 so that I can see what that actually comes out to be. And in this case, it comes out to be something that we need to round. Let me show you that thought here just for a second, because this one does ask us to do some rounding. So I'm going to pull up my calculator and multiply this out so we can see the value. So 4,600 times pi divided by 40. As you can see, it comes out to be a long decimal. But they ask us to round it to the nearest hundreds place. So here is the hundreds place right here. The 3 is in the hundreds place. Well, it's just not letting me write on it. There we go. So I'm going to round that to 400 because the 6 makes the 3 go up. And so my final answer will be 400 miles a minute. So we're really booking it around here. Obviously, if the satellite wasn't moving fairly fast, it wouldn't stay in orbit. All right, so here is our physics problem. We're making a clay vase, and an artisan uses a potter's wheel that has a diameter of 13 inches. Now, they're talking about the part up here that he's actually making it on. So what's the radius? Well, that's going to be 6.5 inches because the diameter is 13 inches. It says it spins at 120 RPMs. What does RPM stand for? Well, that's revolutions per minute. So that goes back to the same thing you see on your car. You got an odometer, tells you how many miles you've driven, and you got a speedometer, it tells me miles per hour. But sometimes you have this other instrument that says RPMs, and that's how fast your engine's turning, which eventually turns into how fast your wheels are turning. So in this case, we have our angular speed, which we are going to find with 120 revolutions every minute. We're going to take the RPM abbreviation and rewrite it so we can read it as a unit. We're going to put that times 2 pi radians over 1 revolution. The revolutions obviously going to cancel, giving us 240 pi radians over minutes. Well, that means that it turned, 120 times around is 240. That's pretty lot of spiral in there. But then again, we're trying to make a vase, so we want our wheel to turn around a lot. So our velocity is going to be equal to that value, 240 pi radians every minute, times 1 radian always goes on the bottom, and what goes on top is your radius, 6.5 inches. Your radians are going to cancel out, so this is going to be inches per minute, unless it tells me to do otherwise. And we would have to multiply 240 times pi, and then go times 6.5. It doesn't say anything about rounding this one, so we just need to get that value so that we have it to work with. And actually, this problem goes a step further, so let's continue to read. Find the approximate distance traveled in 3 minutes. So they just don't want to know how far they went in a minute. They want to know how far they went in 3 minutes. So I'm going to take the distance formula, distance equals rate times time. I'm going to get this rate and plug it in here and multiply it by 3 minutes. So I might want to keep my accuracy for a minute because the answer to this question is not the velocity. So I am going to do 240 times 6.5 times pi and get this decimal. And I'm going to leave that decimal on my screen, but I'm going to come back over here and I'm going to write down 4,900.88 inches per minute, but I'm going to use the whole decimal. I'm going to use answer here so I can use all the decimal places times 3 minutes. And I'm going to come back and I'm going to do times 3 so I have all the accuracy that I need. And now I can round that off, 14,702.65. So the distance is 14,702.65 inches. Now you may say, well, gosh, that's an awful big number. We ought to turn that to feet. Well, it didn't say we could do that, so we can't. We have to leave it in the units that we start with unless they tell us otherwise. Okay, this will be our last one for today. A phonograph record has a diameter of 12. What do you do every time you read diameter? You come over here and you think about, well, if the diameter is 12, then the radius is equal to 6 inches. Now, that's probably not this particular record because this says 45s, and that's an album. An album's a lot bigger. But it's the idea. That's what it means. So our angular speed is equal to omega 45 revolutions per minute. That is the speed at which the record is turning. And we're going to multiply that by 2 pi radians over 1 revolution. Revolutions cancel. So 45 times 2 is 90 pi radians over minutes. Now we're going to find our linear speed. So velocity is equal to that number, 90 pi radians over minutes. We're going to multiply it by 1 radian over the radius, which is why I keep stressing for you to write the radius down, because you've got to plug in the radius of 6. And so we'll do 90 times pi times 6. Because our radians are going to cancel, it's going to give us inches per minute. Now it asks us to find the distance the point traveled in 1 minute. This is the speed at which it's traveling. So we can do 90 times pi times 6 and get 1696.46. But the question says, what's the distance it traveled in 1 minute? So you'd have to say the distance is equal to 1696. Look, the decimal there. Let's try that again. 1696.46 inches, because distance doesn't have over minutes. All right, so as you can see with these problems, they take quite a bit of time. And hopefully after you've watched these 6, you can get started with your packet and maybe do about the first 6. We'll see how those go.